and the Linux kernel memory model. And I'm actually really interested in this one because I don't know about you, but the memory model has always been a very complex and scary thing for me. So I'm sure I'll learn something. With that, I'll switch over and let Bosman give his talk. Let me find the presenter mode button.
Thank you.
You already marked as presenter?
Yeah.
You were here first, so yes. Right, there you go. I will.
Hello everyone. I'm Bo-Chin Feng from Microsoft, and have been working for Linux memory model for a few years. And today I'm going to talk about some improvement I have done in Linux memory model, and mainly for the hard tools. And so, okay. First is today's agenda. I first will talk about a little bit about Linux memory model and her tools, give a few background for those people who is not very familiar with this concept. And then the major part of this topic would be limitation translation, which allows you to translation between different tasks in different languages. And the later one will be the current state of the translation work and what I can do in the future. So let's begin. Okay. So for when the Linux kernel memory model is introduced in Linux kernel, the most important part of that memory model is the cat file, which is the Linux kernel.cat file, and which define the models in cat language of her tool. So for her tool is a memory model simulator, which means it's designed to support customized memory models, so you can write your own memory models in her languages, and the her can help you to exam program with that models. And also, it's a simulator. It's not really run any code, but it could examine the small piece of code which called a litmus test. So as I said, so the Linux kernel has this cat files, Linux kernel.cat, which describes our semantics of how the Linux kernel memory models looks like. And also we have a few litmus tests to allow users, to allow other developers to learn about, how will the program described in litmus test behave in this kernel memory model. Okay, so the next slide. Yeah, so let me just introduce a little bit about how her works. So there are two inputs of her. One is the cat file, the other is the litmus test. And so let's see the left part for the litmus test. A litmus test is a small piece of code, and which is basically similar to normal code. So for this one, the C stand for this litmus test is a C version, writing in C languages, and this is the name of the litmus test. And the second line is the initial block of the litmus test, which may not be necessary for this specific litmus test, because for any litmus test, all the memory will be initialized at 0, and the rest two functions describe what the user wants to execute in the same in parallel on the system. So this is a simple message passing self-programming and retrieved by store release and the load acquire. And the last line is the execution. The last line is exist condition, which tells the herd to verify after all these two functions has been executed on different CPU and whether these conditions could reach or not. So, and the other thing herd take as input is the cat file. The cat file is complicated. It's so if you want to learn the cat file, is maybe maybe you should take a one-day workshop or something like that to write your own cat file. But it's complicated and it needs some practice to achieve that. But for this, so I'm not going to expand details about cat file in this topic. But as we see, there is one rule in the cat files telling that the relations HB, which has happened before, cannot form a circle. So with those two inputs, and we can get a result that it says that there for all the for all the executed candidate, we cannot observe any of the states that's reach the end of which end with these conditions. So another concept for litmus test is that litmus test and herd is that it's actually exam every execution candidate, which means that it's not, as I said, it's not really execute the program, but it can find out different execute candidate, and each different execute candidate represent a type of how the program is actually executed. So so the herd works on the executed candidate. We will see more details in later. And so for the herd to check a litmus test, it will roughly have 3 steps to do that. The first one is it will generate events based on the litmus test. So for example, like for the left, for the litmus test on the left, it will generate 6 events to the right. So those events actually it has a few things, which the type of the event and the notation of the events and the memory. If it's a store, it will have the memory location where it's stored to and the value of the store value. And those two are the initial write events, which is there for the future analysis purpose. So this is basically the first step, generate every event. And those events has relations to memory locations and values and have its own semantics. And then after that, the herd will roughly enumerate all the communications. So by communications, it means if two memory operations like read and write operate on the same memory locations, the read events must get its value from some write event. So for example, there is one read event for y, and so it must, and there are 2 write event for y. So either this one read from here or this one read from here. So there must be some communication, and it cannot for one execution candidate, it cannot happen in the same time, because if one read cannot read the value from 2 write. So this is so so when we enumerate when we enumerate the communications, we actually build up different candidate, and this is one example. This is one execution candidate. So we can see the two read on CPU one. The first one read from this write, and the second one read from read from the initial write. So it's actually the scenario where related to our execution. It's to our exist cloud. Yes. So we want to examine whether we can observe these conditions. The CPU ones are 0 being 1 and are 1 being 0. So that means this one, the first one must read value from this write, and this one must read from the initial write. So this actually the execution candidate which has that condition, but we will see later how the her will rule out this execution candidate. So the third step is actually how her will rule out those execution candidates. So basically, with those communication relations and other relations which brought up by the program itself. For example, in her there is a definition that what is a PO release relation is. So basically, every memory operations before a release options will have a PO release relations from that event to this one. So so remember, we have those conditions that happened before cannot form a circle. So this just if you look closely, it's just the applying the rule in Linux kernel .cat file. So for example, the propagation relations and the internal relation actions, the intersect of that. This one stands for intersect, and this intersect of that is happened before, and this one is called from read, which basically means that a read happens from before a write. So like this, we can so given that given the communication we see in previous slides, so we can make sure that this write. So since this read does not read value from this one, so it must read value from the previous write. So this read happens before this write. So there will be a relations from read from this read to that write. So something like that. It's just applying the definitions of different relations, and as a result, we can see that these relations. So there is a relation. So this one, the relation combinations is actually happened before. So which says that the second read is happened before this first read, and another thing is that this one is also happened before. So means that this read is happens from this read. So that means it cannot happen that way. And we also, in her tool, we also say this cannot form a circle. So as a result, the her will rule out this execution candidate based on this check. So this is basically how her work. Okay, so does anybody is anybody not quite familiar with this? Does anybody have any questions about this, about how her works? Okay, let's continue. Let's move on. So we have, as we said, we have a few citizen tests. Do you have any question?
No, I just was just getting the camera back on.
Okay.
No.
So we have a lot of citizen test example you can try out is either in the kernel directory or in Paul's GitHub archive. Try out, and also please note that the herd also support assembly litmus test, which, for example, this one is the of litmus test in which similar in then which is similar to the dependency. So it's and her can actually examine the whether these conditions will be true after all dust is settled down. So please note that the cat file that handles this type of litmus test, which is written in assembly code, is actually built-in built-in functionality in her tools. Yeah, it has a different cattle, but the cat file comes along with the release of her, so it's kind of the internal to her itself. And also, I think the memory model for for ARM64 is actually done by people from ARM. So I think this means that other than the cat file in Linux kernel, which directly describes the Linux kernel memory model, is done by us. We have two different people working on two different memory models that both of them could be understood by her. So yeah, that's the litmus test for assembly code. Okay, so now we have small introductions on Linux kernel memory model and her tools, and so with the Linux kernel memory model cat files, developers can use the litmus test to kind of learn that memory models, and also can try out to verify he or her design on the on some critical code for the subsystem, and also can learn the semantics provided by for learn the semantics modeled, which already modeled by Linux kernel memory model. There are some, maybe a few primitives like semaphones or mutex, which is not actually modeled by memorized Linux kernel memory model. So we can now try litmus test with that primitives in Linux kernel memory model. But please note that the cat file in Linux kernel is actually based on a few of us understanding of a small group of people, and which is experienced in parallel program stuff in Linux kernel, and after we audit every primitives, after we audit the current implementation of every primitives, and we also try to people's requirement for those primitives, and we and we also try to understand the primitives of the try to get the requirement from the other developers of what their expectations on those primitives, and we wrote those CAD files. We wrote the CAD files of the Linux kernel memory model, but there is no guarantee that this CAD file will be the Linux kernel memory model will be implemented correctly. So that's one thing, because the CAD file only design the semantics of the memory models, but we don't have the tools to kind of check whether the semantics is implemented correctly in this kernel. So that's one thing, one problem. The other problem is that the other small issue is that we kind of sometimes we already have a lot of litmus tests, as I mentioned before, in written C, and we want to have want to have the similar litmus test in other languages, maybe in order to talk to in other languages means the assembly code. Maybe we want that in order to talk with hardware people, because if you show the hardware people a bunch of C code, then he may not understand if the one does not work for Linux kernel, he does not understand what does SMP store release means. So you had to give them to the assembly code so they can understand. So maybe for that purpose, so which also introduced the requirement for translation litmus test in C to a litmus test in assembly code, to at least requirement and the motivations we need to examine how we can translate litmus test from C to assembly code. And we have those tools, Jingle and Zensteam, to help us to do the translation. And so first we'll go a little bit about how Jingle do things. It's so it's similar to input. One is the input litmus test, the other is a sim file, and the Jingle translates into the litmus test in other languages. Please note that I forgot to mention in previous slides that when the herd generate events based on litmus test, it's actually use a parser to parse different languages, so which is the similar parsers which used for Jingle. So basically, when the Jingle saw a litmus test, it will pause that litmus test and generate a few IRs that the Jingle or herd can understand. And the sim file also, the sim file has the rules to translate from one to one IR to another IR. So that's how the sim file gets the Jingle to translate the litmus test. So let's look at how is a sim file look like. So for example, this is one from C to ARM64, and it's for example, it says that when you saw this one in the AST or the IR of a C litmus test, translation to assembly code. So this is how the translation is done, and you can add your own translation rules for different this kernel memory ordering primitives, and this one is for the loud acquire and this one is for stories, and how the jingle works, and if ideally that the sim files will be maintained by architecture maintainers, and we can whenever the this kernel memory model change or the underlying implementation change, we can use the jingle to generate all those. Remember, we have a few litmus tests in Linux kernel memory model directory that describe the expected behaviors of Linux kernel memory model. So we can use the jingle to translate those litmus tests into a and check with the herd using the architecture specific cat file. So in that way, if we saw there is anything change, so we know that there is problems in the either in the implementation or in the memory model. But there is one problem is that, as we can see in previous slides, to define the translation rules, we need to write the translation rules one by one for each primitives in Linux kernel. In the Linux kernel C version, we need to write the corresponding translation rules, and that is a lot of work. And I'm not sure that whether architecture maintainer will take that. Will take that as their maintained work. So we can improve this situation a little better by introducing another one, which actually generates the sim file. This is gensim2. So it has take two files as input and generate the sim files we could be used for Jingle to generate to translate this test. So there are two inputs for the gensim. One is the .call file, which is kind of serve as actually architecture independent thing, similar to what we have similar to Linux atomic.h. It's define the general rules how we make another synchronized primitives based on the other one. For example, we know that RStudio dereference is just another name, a same name for read ones, because we now require read ones to carry the address of the data dependency. So they are similar one, and we can say this is the same one with this ID function. And also, if in the architecture specify, we define how we can make, we can define how we change a primitive from a relaxed semantics to a query semantics in the architecture specific file, which is the .map file. We can specify that. So we in general, in the call file, we can say that SMP load acquire is nothing but we add the acquire semantics of a normal read once, and it's similar for SMP store release. And for the this one, the typo is to be exchange relaxed. So for if we want to add translation rules for exchange, which is the fully altered version, and we can, if we have a function that shows how we could lift a normal exchange relax to a fully altered one, and we add these functions to generate those rules for the theme file. And the next slide is how the map file should be defined. So it defined the primitives, the building blocks for those symbol synchronization primitives, for example, like read ones and write ones. And also it has defined a function like symbols. So remember we in previous slides, we lift write ones with a release, we got SMP start release. This one is simple. If we have those functions and if we find we call release on write ones, we actually use this to do we actually will use this to do a find and replace on the right hand of this expression. So see, this one is this table. See, the one is a store, is a normal store, and if we find this normal store, and we can do the find and replace, we got a release store, a store release. So this one is lifted into the store release. So we can have multiple implementation for one functions, which will try one by one and see if there is a match. If there is a match, it will do the final replacement. And also those like procedural functions can be composed. This function, the full function actually change rules for a relaxed version, so relaxed primitives into a fully altered one, and it's actually done by 3 processes. First, we change that to acquire, and then we add acquire semantics, then we add release semantics. Then if it's a require release semantics, we can see if we can add another find and replace, make it a fully altered, which is called full on acquire release function. So this is just a simple introduction to how the .call file and .map file will work to generate how the actual implementations for ARM64 and PowerPC of the full on acquire release, and we can, if anybody is interested, we can look at it later. So with that, we can actually achieve the translation from one listening task to another listening task. And we currently support Linux listening task to ARM64 on the Linux listening task to PowerPC. And atomic APIs are partially supported because there are some because the one I'm using to test doesn't have all the atomic primitives, and handling some of them will be tricky. And so I have them partially support. So if the listening test, if your listening test has those APIs that I'm not currently not support, it probably cannot do the translation. And the RCO APIs are not supported because you cannot do a similar translation for RCO API. RCO API is complicated, and if you find a way to implementation RCO read log and RCO read log with a few assembly code, please feel free to reach Paul McKinney and tell him your funding. And So Splogs are translated as a simple Splog implementations mapped to basically something like compare exchange, but this is not accurate, and also due to the limitation of her, her will check different result based on the her will get different result on the different version on the C version and the SM version. This one is because her, as I mentioned previously, her actually kind of enumerate every execution candidate, and for logs, it's actually not. It's actually a little bit tricky because if you write a little test which has a deadlock in it, and if it's a complete one, and the herd may just doesn't notice the case where deadlock really happens. In other words, the herd only checked the execution candidate where there is no deadlocks. So that's one limitation of her. And if we translate a log, a little test with C code which has a Splog and into assembly one, and there will be a so for real the logs in C little test is not real log. It's just an annotations put there saying that this is a log event, and her will generate log event and analyze it afterwards. And for the assembly code, there is no log events to generate. So I currently have to generate the log, how to translate the log primitives into assembly code, which implemented simple logs. But since her can now, if you understand how her works, you will know that if there is multiple loops, then the herd will cause her a lot of time to check the execution candidate. Maybe some infinite, maybe the time is infinite to check for some little test. So I don't see there is any way you can do with the little test with Splog for the code. So that's the current state of the translation functionality. And the future work is of course support more APIs. And if I got those, if I can, so one of the gap of actually having this in kernel is that I'm not sure why it's kind of learning effort to learning how to write the .co file or .my file to learning another tools. I'm not sure I provide the best interface for the one who really implemented the atomics or other APIs to use. So it's going to be some discussion with them and to see whether the semantics they think is good, and whether they can make sure that the map file is synchronized with the actual implementations in kernel. So it's going to be some discussion between them. So this is, if I get everything almost working, I'd like to hear about their opinions. And of course, if this one doesn't work, we can try another different approach. One being using Lisa. Lisa is a litmus test instruction set architecture, which is another IR to as an intermediate languages to do the translation. But then again, that will require the architecture maintainer to learn about this. So we'll see. And so I would like to show you you guys some demos to how to do the transition. So feel free to ask any questions while I'm doing the demo. Okay. Okay. So as you can see, we generate two symbol ahead. This one and this one for ARM64, and I changed it a little bit. So usually usually, as you can see, this script, it will check with the normal C version of little test, and I do the tricks by using this to generate the unspecific, to generate the assembly code first, to generate the assembly one, and check with the assembly ones. This is not the usual little test; it's the generate one. So and this script, the check little test script, along with the overall script will check all the little tests in this directory, and to see, as we can see there, have the expect result. So which sorry, which means that the memory model actually expects this clause. So we actually so with this script we can generate the hidden test first and then run with herd. Note that herd can handle assembly little test, and to check with the result whether it's synchronized, whether it's the same as the expected result for the citizen test. So running this. Okay. As you can see, if you run if you run the different tests, run the checks on normal C, all the tests will say there will be no the error message here. But now we have still some issue. Some of them is because we cannot do translations on this. We cannot do some of them will be is that we cannot do the verifications because for this one having logs in it, so the result may be not accurate for this one. And remember, and for this one, has the this one has the RC read log and the RC read log in it, so it cannot be generated. And for the one we can see, for example, this one. Under this one, we can see the version and the result, and one is the generate version with for ARM64, and as we can also see that time, this is the execution output for those things. So yes, as we can see that we can, in this way, we can translate one little test from C to ARM64, say, and we can use this script to we can examine the result for both execution tests, and we can verify whether they match the same result, which means that our implementations of those primitives stay the same with the semantics we described in the Linux kernel memory model. Okay. I think time. So anyone has some questions about this?
Yes, please put the questions on chat or come in on video and ask your question.
So I'm still also logged in at the Rocket chat. So if you have any questions, you can reach me out. Everybody can reach me offline. Marco is typing.
I'll ask a general question. Did you find any cases where the Linux kernel memory model was invalid on any of the architecture you looked at?
I was working on an operation model. Think about this. Operation model. I think that you probably could read the original Herd paper.
Right.
And the Herd paper, will describe actually the Herd paper describe the operational models of this of the Herd itself, and but in the Herd paper they only describe the memory model for ARM64 and PowerPC. So I know there is a few operational memory model tools for ARM and for PowerPC, but I don't know exactly. There is some one for this kernel memory model. So
okay. There was one question on the chat from Marco. He said, curious to know if anyone has working on an operational model of the LKMM.
I think, yeah, Buku just tried to answer that, so thank you. I was just curious because I had some ideas how to potentially use an operational model rather than an axiomatic model. Because I mean, with axiomatic models, you usually have to enumerate all the possible, I guess, all the relations. Whereas an operational model, you can just execute. And I had some ideas, and I was thinking, okay, that was actually in the context of KCSA, and I was trying to figure out if I can find a way to detect missing memory barriers, and I somehow led me to an operational model. That's why I was curious.
That would be interesting, yeah. Okay,
so I remember that. Actually, the memory model defined by in this kernel cat file is actually having a small operational model. So it's basically you have the things like the events like propagations from one CPU to another, write propagation from one CPU to another, and so I think maybe based on the based on the operation model described in the I can't remember. It's the explanation.txt. Maybe from that file you can build up operation models that actually describe the operation models. So yeah,
Thank you. Yeah, I think that's fine. Maybe we can also discuss offline. I had another more general question if we have time. Do we have time?
Yeah, we have about 5 minutes left.
Right. So this is a more general question about the LKMM, and I think all the relevant people might be in the room. And essentially, it seems there's a strict and a relaxed LKMM these days. And essentially, I'm wondering what can we do essentially about the gap between the current LKMM and what the wider community currently wants. My worry is that essentially it's becoming more and more difficult to use the LKMM as the de facto reference to point people to when writing concurrent code. So do you think, or do you think we'll eventually evolve to something, or how will this evolve? I don't know. Like, I don't have the answer.
I must defer this question to Paul. Paul, can you?
I wish I had a good answer. Some of the changes that KCSAN did, which, as you say, were responding to the community, are things one might imagine putting reasonably into LKMM. Others might be more difficult. My personal approach, right or wrong, is kind of wait and see how it plays out and not be too eager to move all the models all at once. But yeah, you're right. Longer term, we'd kind of like right now, KCSAN is the weak model and LKMM is a strong model. My hope would be that we'll have some things in both directions to converge them, but that's got to be future work at this point. I'd invite anybody else on the maintainers list to put their 2 cents in if they'd like.
Thank you. Yeah.
Or not if they're shy or shouting at the mute button.
Yeah, any more questions? Let's see. Well, with that, I think we should say thank you and take the 10-minute break before the next session that starts on the hour.
Thank you. Thank you, everyone.
Thank you. So what is that shirt? It looks like it's got little arrows in it. Can't hear you. Your audio's not working. It was kind of my trick to get you to give an audio test. Oh,
Right.
there you go. Yes, finally.
It was on 0 volume.
I've done that before. I've done everything like that before. So it looks like it's some sort of like political shirt about arrow slings and arrows.
I just think, well, a couple, and she has like a bow. And arrows
okay.
to his body.
Oh, okay.
I do. Yeah, I picked that up years ago somewhere.
It's very cute. Are you ready to start? I will. Okay. So the next talk in our free track today is by Benjamin Berg, talking about resource management in the GNOME desktop. And I'm interested to see, because I've got some familiarity with Cgroup and the challenges of trying to deal with server-side and embedded applications in Cgroup, and I'm interested to see how it will work out on the desktop. So please welcome Benjamin.
I hope that I'm not going to disappoint you. So yeah, we have been looking a bit into resource management in GNOME and also cross desktop in general. So in principle, it's mostly about CPU memory and I/O access, obviously, from our point of view for now. And the current distribution model is that we have all the applications just competing against each other, and you might do some things with ulimit or process nice values and similar methods, but this is all in the process level. So we are treating the processes equally in the desktop generally. So why shouldn't we go further and use all the Cgroup features, basically? So in that way, we could start treating all the users equally. If you have one user using a lot of resources, then this shouldn't penalize any other users on the same system, ideally. If you have multiple applications running, if I have, for example, a make J16 running or something in a terminal tab, why should my browser be slowed down if it's just trying to render a video or something like that? Why is it competing directly with all those 16 other processes? And also, in general, we want to keep the desktop responsive in case there's lots of I/O excesses or similar situations. And if we already start with these kinds of things, we could also start to consider other things we could do on top of that, like discriminate the processes based on other issues, like whether the service is important or not, whether the user is active so that the active user gets more resources than any inactive users, or users that are logged in through SSH and versus users that are local. Or we could even start doing things like prioritizing an application that is currently focused. I'm also wondering a bit whether we might do power management features in the future. That is not something that I've looked into so far at all. So let's do a quick demo. This is something that David Edmondson of the KDE people. So most of the things I'm saying today is actually cross-desktop. When I initially, now I think I remember what I forgot. Yeah. Okay, let's forget about that. I'm on Wayland right now, and the screen sharing doesn't work. So what I was going to show is a video with that David Edmondson created as a demonstration, a proof of concept, where you can see that the running application, which is just a spinner spinning, and you have two of them, and the one that is selected currently, the window, it will spin faster than the other one. So what they're doing is just simply changing the CPU weight of the process, and it starts to run faster when it's selected. So these are the kind of things that we could be doing with Cgroups. And then something that came up in Fedora a lot in the past year or so was that thrashing and OOM handling. So there were a lot of discussions there, and apparently the shell and graphical applications, we're still run into situations quite regularly where the desktop may freeze completely. And so the current approach is there, and people have been trying a lot around that, is to use certain heuristics to try to find these, figure out that we are coming into a situation that's bad, and then doing something about it. So the general approach quite often is memory available based. So this means early OM. This has been adopted in Fedora 32, I believe. So then we have a PSI-based approach where we check the memory pressure information that is exported to procfs. Which is a method employed by NoHang. And then we have also been going to faster swap. So the thing here is that with memory available based approaches, we, in my view, what we effectively do, please correct me if that is wrong, is that we ensure that the kernel has enough main memory for file caches. And by doing that, we ensure that we don't end up reloading binaries and refaulting executable code from disk all the time. And because it's a measure that's always up to date, we can just simply pull it every second. So early OM as an approach that uses memory available should be a pretty fast option at detecting when we are coming into a situation. And then we'll just kill some applications to rescue ourselves. The next approach is the pressure information, which is, in my view, the better approach because it actually measures what is going on. However, it generally needs to sample across a period of time. And we are looking at, I believe systemd OMD is using 60 seconds or something like that. So we're looking at way over 10 seconds for time frame to respond, which is actually really slow if you consider a graphical desktop where the mouse is moving and you want to interact with it. So people are looking into that. And then obviously we can also try to make swap faster, which is something we are doing in Fedora now too, with swap on ZRAM. I think it was swap on ZRAM. There are multiple approaches there. So apparently this also improves the interactivity. I haven't done that many tests myself, but people have tried a lot of different options. And there were long discussions about early OM and how to do this correctly. But in my view, it's not really all of these are not really perfect, because either it's too slow, like PSI-based approaches will come too late. Faster swap is probably good, but will not rescue you in all situations. And memory available, there have been quite a lot of flame wars around that, whether it's just too aggressive and whether it will kill applications without any need. So thinking about it, what we really need is to keep the shell and the task manager, like the important stuff that the user really needs to interact with, responsive. And then the user should be able to identify and kill the problematic tasks. And we might also want to be able to isolate runaway applications. So really, this should be possible to do with Cgroups. So if we have all these important session applications inside a Cgroup, then we can set the various options, like especially the memory low value, maybe also memory min, CPU controller, I/O controllers, and we should be able to contain the thrashing part to a different part of the system, so that the user can still interact with the graphical desktop. And if we are able to identify and kill problematic tasks, then automatically we can also help the user recover. And this is something where systemd or MD and using a pressure information-based approach should be completely fine. So if the user hasn't reacted themselves within a certain period of time, we can then react for the user. And if we are placing each application into a Cgroup, we might also be able to do something more proactive with that. So this has been ongoing for quite a while. We're using systemd in GNOME, and everyone else, I believe, are also basically moving to systemd to use this. And we were not ready until quite recently. So we started, I think it was mostly last year, where we pulled in a lot of the things, and this has been a development that's been going on for quite a while. So systemd user instance has been a thing for quite a long time. Then dbus started being migrated over, and we have a per user session bus now these days. Then when we started to run applications outside of the session scope, I'll show that in a bit. We started to have to adjust a lot of user space systems that weren't unable to track sessions properly. We needed to port to service. We needed to start to port GNOME itself to systemd, and there are still some open issues there. And then also important applications like VTE, the GNOME terminal, these days creates a scope for each tab, which means you get nice hierarchy. And obviously other desktop environments are also working on that. KDE I've been working a lot with the KDE people mostly, and the systemd people, but I'm also aware of other desktop environments making things of their own. So eventually we talked with the systemd people, and it turned out that we should probably create some conventions on how we are using systemd and how we are grouping the sessions. So what we ended up with is these three different slices inside systemd. So what we want is we have a session slice where all the essential services go in, which is basically the graphical session without any application running. Then we have app slice for all the normal application, and then we also have a background slice that for all the irrelevant stuff, like, I don't know, probably indexing. For example, Tracker is indexing your files in the background, or backup jobs, something like that could go in there. Another thing is that we also encode the application ID in the systemd unit name, so that we can then go from systemd Cgroup name, which is the systemd unit name, to which application is actually running at the time. And then we are able to tell which application a process belongs to, which might not be obvious in all cases if you have a browser that starts a couple of extra processes to render things. So this is an example. of a running session. So you have group Cgroup FS, systemd splits that into system slice, user slice, and then user slice, you'll have a slice for your own user, which is in this case UID 1000. So you have user 1000 slice. Then my graphical session, which is launched, will be launched in a scope by GDM, by your login manager, or more technically actually login, which in this scope, it will execute the X server if you're on X11, otherwise it won't. A few other things may be executed in that scope, like the tiering and stuff like that. But after that, from that scope, what we in reality do is that we start your session using systemd, and we'll just wait for the systemd running session to quit. So everything else is actually inside your user manager. And then we can put the GNOME shell into the session slice, and we can place everything into session slice. And all this is relatively simple to do using a few systemd configurations. The hard part there was actually migrating from just executing everything to using systemd to run everything. So with that, we are now able to just modify the Cgroup attributes for the applications on the systemd levels. We are able to, which means we are able to manage per application resources in principle. An example of this would be task managers, for example. So GNOME, I have an example of KDE, what KDE did, which is David Edmondson tried to did this. No, didn't try it, he did. So what you can see here is that the Spotify application, it's grouped by the Cgroup name, and then it has all the various processes listed from the Cgroup information, and that way you actually get a proper memory usage information. Implementing the same thing in GNOME usage, which already tried to attribute it to the correct application. So you have here, what stands out is web. So it's the Epiphany, the GNOME web browser. So you can see that it's at 567 megabytes, and you can also see that the system, everything it can't attribute properly, is 3.4 gigabytes. And then if we start to just use the systemd Cgroup information, we suddenly see that web is now at 2.1 gigabytes and system is only at 1.8 gigabytes. So we are able to correctly attribute all those spawned processes that Epiphany have or the other browsers have to the correct application with that, which is already a huge advantage. There's still a few things that we need to do. Some of that is just migrating more stuff to systemd so that it becomes cleaner. One of the main example there is XTG auto-start applications, which we would like to start using a generator, so just let systemd start them all. Right now we are still starting them directly. But more importantly, when applications are launching other applications, for example, I don't know, you have a chat application open and you are clicking on a link and your browser hasn't been running yet, then that browser shouldn't end up in the same Cgroup as your chat application. And right now, what applications are doing, they're just spawning each other how they like. But most of the time, they are luckily using the appropriate APIs. So what we need to do is we need to fix the APIs. KDE has already done this. So you have an application launcher job and command launcher job, and I'm not sure if they're actually starting it using a systemd service, transient service, or a transient scope. So they just spawn the process and then move it over into a new scope. But it's there, and in glib I have a merge request open, which is unfortunately still pending, which will do the exact same thing. So it will create a new scope for each application that is launched, where application is defined as an application that has a desktop file, basically. So it's there. It's not wide. It's not there. There's still issues there because you might end up with the wrong application, the wrong Cgroup, and stuff like that. So it's not perfect yet, but it's already quite useful, and we already get a proper Cgroup structure in most cases. And so we can actually start using this to do something useful. And the motivation to do something around this was mostly for me, was mostly the out of memory thrashing scenario, where I figured that we have all the low-level functionality these days, and we have Cgroups, but we are not using any of those features yet. So we should just enable them, and it's easy to enable them. So let's just do this. So I wrote User Resource D, which is a pretty simple piece of software, really. And all it does is like fix up GNOME a little bit, because there were still we were still developing it, and the system conventions weren't there, so we are fixing it to make it more look like the system conventions. And the main thing is that just we enable CPU and I/O controllers for the applications, which is just one option in systemd, basically. Then also create a small daemon that tracks the active session on the graphical seed, because you might have the graphical session and stuff like that. So the graphical greeter might have a session, and so it's actually quite likely that you have multiple sessions running. So you don't want to just give out resources to any user that exists on the system. So track the active session, and then just allocate 250 megabytes of memory load to the active user, and kept that at 10% of the system memory, just in case we are on a low system. And then forward that to the session.slice that we have already previously defined, and which will then guarantee that GNOME shell and all the important processes will receive a good share of memory and should remain running even in a low memory situation. And then we can also set CPU weight and I/O weight for the active user, and these kind of things, which is just a small boon. Note that I'm currently disabling the memory controller for all the children of session slice, so it's on the lower level. But the only reason for that is that systemd doesn't currently set memory recursive prot, and I didn't really I could also probably use the default memory low option that systemd has, but it's this was a sane solution, and there's a pull request now. System will be changed to include the mount option, and at that point we can just drop that. So that's not a big deal. So yeah, what we are achieving there is that we are now letting all the applications compete equally for CPU using the Cgroups. With the active user, will get a greater share of CPU. The core session should get a protection from thrashing. Unfortunately, I've tried to do a few tests with regard to how good the protection is. I have here good reports. I haven't really been able to reproduce a good scenario to test this myself. If anyone has a good scenario to test this, I would be really grateful to hear about that. Anyway, so there are a few things that are still a little bit problematic in my view, and the main problem that I see is the I/O controller, and which is not fully configured. So the I/O controller, the problem that I'm having there is that one, systemd doesn't have all the options yet, so it's not actually setting the I/O cost model so far, as far as I know, and as I understand it, that means that I/O weight may not properly work. Another issue is that in a typical laptop scenario, we are using Lux and LVM and stuff like that, and also file systems like X4, and apparently that's also not working very well with the with the I/O controller. So I'm expecting that we are not fully utilizing the I/O controller, which means that if we end up swapping, which we will do to some extent, even with the 250 megabyte allocation, we might still run into issues if there's a disk-heavy other application running in the background. then we have a new daemon, which is probably not something we want in the long run, but that's not a huge deal. We'll just need to absorb it into something else. The main problem is figuring out where it should live, because it probably should go into systemd. The obvious choice would be systemd log ind, but it doesn't quite fit into it in my view. But it's not a big deal. So it's just a tiny daemon that's running there for now. It's currently also completely opaque for the desktop environment. It's just passing out 250 megabytes, which might not be the right amount in all scenarios. I'm not sure what to do about that. It's probably good for a start. But in the end, we might want to have desktop environments choose the memory allocation and let them manage parts of this. But I think we're still moving in the right direction here. And in the end, another problem is that, as I explained earlier, the X server is running a different location in the Cgroup hierarchy, so it might not be protected. It works best with Wayland right now. But I think it is, as I said, I think it's a good start, and it should be replaced by other things and absorbed elsewhere. But yeah, we are actually going to ship this in Fedora 33. On Fedora 32, you can also just simply install it. I mean, it's a very simple program, really, and just a few systemd configurations. And you should not notice any difference in most cases unless you're actually looking at it and comparing the different Cgroup things. So yeah. I'm just seeing a comment there that GIMP and Darktable is not going to like these restrictions. I guess we'll need a user-friendly way for users to tweak this per application. I don't think this is a problem, because right now, all we are doing is putting them into a Cgroup and enabling the Cgroup controller. Unless they are actually in competition with other applications, they are not going to lose any resources. So if you're just using GIMP or Darktable, and nothing else is actually trying to use resources, you'll still get full all the resources that you want on the system. So I don't really expect that this should be an issue. Oh, someone else asked whether why evolution calendar takes 2 gigabytes. I've had that question before, and the reason is that is actually evolution, not evolution calendar. It's misaccounting that, and it's all my email in there. So that was just the wrong application picked by the I'm not sure why, to be honest. Yeah, I'm wondering about going forward is whether systemd OMD will actually work well for us. I've not yet tried it. I suspect that it's, again, hard to try. It probably should be able to detect problematic workloads. It's more of a question, should we just go in for a kill, or should we try to give a desktop environment a way, like to interact with it? So basically tell the user, what we could be doing, for example, would be, okay, we have identified a task that's problematic. We could just, I don't know, freeze it for a start, then I'll prompt the user, do you want to kill this or not? And then the user can decide, like, continue or kill. We could probably do something like that in the long run. I'm not sure. Maybe we should also set other things like memory high, CPU max, or something like that, which would piss off the GIMP people, I guess. But I suspect that the right thing is to just go ahead for now, configure systemd OMD, and then see whether there's any fallout and people are complaining that it's killing too many processes. It's hopefully good enough, and if it's not, we can still bolt on interfaces on top of it to make it do what we want. At least that's my hope there. Another thing that's probably a question for you guys and for the Kernel Go folks is, I'm currently setting mainly CPU weight, I/O weight, and memory low. And in my view, that should give quite a lot of guarantees. So we have CPU time guarantees. If we have the I/O controller working properly, then we have fast page faults, because we'll hopefully get prioritized the swapping I/O and the file reloading I/O, and hopefully with the memory low allocation, we'll also have to simply not be reclaimed that often. So I'm hoping that the guarantees are good enough, but if there's any suggestions on what to add, that would be useful. And yeah, the main fear that I have is that we might be crippled by the I/O controller not working well enough on most setups currently, due to Lux, LVM, and X4, which are still very common. And even with Fedora moving to ButterFS, we still have a Lux device underneath in most cases. And then why we need, as I said, we probably need system to set the cost model and stuff like that. So I think we are like, everything is looking good in general, but unless the I/O controller is actually working and completely doing what we want, most of the advantages that we have that we are getting might be lost again if we are still doing some swapping, which we are going to do. And then we might still end up with the desktop freezing and stuttering in low memory situations where the system is thrashing. And yeah, so what else should we do in the future? I mean, one example was prioritizing the application that is currently focused, which is a really simple thing to do. I should have probably done a demo GNOME shell extensions to do that, because all you need to do is figure out the process, figure out the Cgroup, and then set a few properties through a dbus. And one thing that I'm really wondering about is power savings, because like, I believe that mobile operating system might be freezing applications in the background. Then I've seen discussions about changing timer accuracy, or just helping developers to identify problematic applications that are actually doing too many wake-ups and stuff like that. And it might actually help having the Cgroups and then being able to easier follow what's happening in for multi-processed applications. But yeah, if anyone else has ideas, then I would be welcome. And that's basically it from my side for now.
Okay, thank you. I'm gonna turn on my camera here. So I have one question, which is
Sure.
a little naive. Is there any interaction here with Cgroups and networking, as in, you know, I've got a video app that's on doing networking and I really want it to not drop frames versus something else that's downloading something in the background, or...
That is nice. No, I hadn't even thought about networking, to be honest, because
I mean, networking has caused stuff, but it's not really integrated all the way up to the desktop in any real way. I mean, people hacked ways together. I was just wondering if there was something.
I wonder, I mean, if it's just setting a few attributes in the Cgroups to implement this, then we should be able to do this quite easily.
Yeah, I think it's kind of a little more end-to-end kind of thing. You have to have the Cgroups and the underlying infrastructure in place on the desktop to get that to occur, but it should be possible.
Yeah, but we are getting there, that we have all applications inside a separate Cgroup. So as long as we know which applications should be preferred, it would make sense. Though I could imagine that this is the problematic thing is that it might be hard to figure out the heuristic to use, because it won't be focused applications. So if I have like this video chat running here, big blue button, and switch desktops because I'm trying to demonstrate something, you probably still want to give the resources to big blue button, even though I'm switched away.
Yeah, it kind of brings up the bigger problem of like, how much does the user have to interact to give what he wants or she wants, versus just make it work, damn it.
Yeah, exactly. We generally go to just make it work, damn it. So we want something that works out of the box without the user needing to interact and optimize this. Though what you could do is, if we know that a certain application has has high needs, then we could ship a configuration that just modifies that application. that would probably be the sanest solution here, for it to ship its own systemd service with a higher priority for networking.
Okay. I'll get out of the way for the next question.
Are there any other questions?
I'll ask the dog food question. Are you running this day to day, and do you
Yeah,
feel like
well,
it makes life better?
to be honest, I don't think I'm noticing the difference. I'm currently running it, yes. And you notice that like it's easy to create a test where we already tested. Like if I SSH in to another user or something like that, and then run stressng on one user and then stressng on the other user, then I'll see that it'll balance out differently. And have you tried running it on a bad netbook? No, I have not. Duh, that's why I added the 10% memory limit, so that it won't like try to give the GNOME session everything. Too much memory, so that the kernel still has more room to do things. Because I was figuring that giving a quarter of a gigabyte on a low-end machine might be too much. If you only have 1 gigabyte of memory, then it's probably better to err on the side of handing over the kernel more leeway in making its choices. So George says that he notices the difference. So I'm wondering whether that difference is positive. Okay, so Jeff says that LTP OOM tests may be useful test cases, and yes, that might be a good idea. I haven't been aware of it, but I think I have a look. Because actually, like trying to exercise scenarios where the shell will hang and figuring out whether it helps or not, and how good it helps, and whether we might need to adjust the memory limits, or maybe we should also set memory.min and not only memory.low. Then yeah, that would be really helpful. So I'll try it out. And George says that it's actually helping him to keep its applications responsive. So that's good.
What's the smallest system you've tried this on?
To be honest, I'm running it on a 16 gigabyte system.
Okay.
So yeah, that's not very small.
Okay.
But I wonder whether there's any interest in having some more discussions. We can probably do that on Friday after the talks that we have in the what's the called? We have a track for the desktop and applications.
Okay.
Or
Got 2 more questions here.
yeah, I have not tried it with big applications explicitly, like GIMP. I really don't expect. I personally don't expect any difference, as I said, unless you have something else running at the same time. But all we are doing is reserving a bit of memory for the session, which is not really too much overall, if you think about it. Was there another question?
There's 2 more questions soon to be the famous typing.
Oh, you mean the typing? Yeah, let's see. Something comes up.
The only desktop app I've had trouble with is if I ever do any YouTube video encoding.
Right.
I mean, those just sort of might as well go away and get coffee or something.
Yeah, but in that case, it should help because then it's probably contained, I don't know, in some, it'll be now in a C group, in a separate C group with the controller enabled.
Right.
You'll at least like be able to open your, I don't know, your email, and it'll get enough CPU time.
You can read the next question.
What is picking which C group to kill if you go into low memory? Do things like in scope on the desktop factor in at this point? So right now we are not actually doing anything of this. Right now we are still in the regime where we use early OEM, which is deciding based on memory avail, and it'll just, I think it'll basically trigger the OEM killer, the kernel OEM killer. But what we'll hopefully do very soon is that we'll enable systemd OEMD once that's merged upstream. So for Fedora, I'm looking at Fedora 34 there. And at that point, we'll kill the C group that is doing the most thrashing. So we are looking at the memory pressure information, and it's also looking at the reclaim rate. At the page fault rate. So that basically, if the application is thrashing, then we'll kill it. And it'll just kill the worst offender in that regard. Though, if someone, I don't know, if someone has input there, I guess you could have certain workloads where you expect thrashing. I'm not sure if that actually exists. And whether we might end up, I don't know, killing a backup program or something like that because it's doing a lot of I/O. If it's doing it in a way that triggers the memory pressure.
Well, is there any way you can do something that's not killing to it, the equivalent of what a phone power saving does, where you basically end up swapping the whole program out and just getting its memory back, but it's still there in some form?
Right. Not necessarily killing it, but just setting like memory max or something.
Yeah, so it's basically just crawling.
Yeah, we could probably do that. I'm kind of hoping that for now, we can just go systemd OEMD and it's going to be good enough, which means killing.
Yeah.
Because that's going to be simple, and I like simple.
Yeah. Yeah. Whenever you get in that domain, there's never a good answer.
But I'm kind of expecting that there'll be a few applications that need to have their own systemd configuration to opt out or opt in, or change a few settings so that it's fine-tuned to their use case. But we'll need to see, because we'll only see that showing up once we start shipping that, I fear.
I'm waiting for the last questions here.
Yeah, people are typing, so that's good. Take your time.
You can turn your audio on and ask a question that way too. That will. Are we waiting for something that's never going to happen?
Yeah, maybe. So yeah, I hope that this is going to be helpful overall. Though, yeah, it's going to be more work to actually get this all perfect, including like the X server, because I fear that some people are going to continue using the X server. So I'll probably need to look into how to make GDM execute the X server as a systemd service rather than just spawning it, which might be fun and stuff like that.
Yeah, I mean, this all looks very useful. It may very well be that, you know, the
and I really
issues...
hope that the I/O controller will do what we need it to do, at least in the future. I've heard that it only works well with Btrfs on a plain disk right now, so not sure if that is true these days.
Well, that fits Fedora's model, but
not really. I mean, because I, for example, have an encrypted disk, so it doesn't. If it
oh,
doesn't
yeah,
go
that's
through
true.
that, then I'm screwed anyway.
Yeah. Okay, well, I think we'll just call it good and take the break. If people want to keep going in the chat, they can keep going in the chat, and I'm sure you can get a hold of Benjamin afterwards. And he mentioned there was a later desktop session, so I'm sure you'd be there too. Thank you very much.
Yeah, I'll be around. Okay, thank you.
Thank you.
Hi, Kevin. Can you hear me? I gave you presenter rights. So,
Hello.
okay. Hi. You have presenter rights. Would you like to test? Just pass the slides and something like that.
Let's see. Hello.
Hello.
Yeah. Seems to be working. Although, yeah, that's good. I think that's all right.
Oh, great. So I want to start the session in 2 minutes. Okay, is that okay for you?
Yeah, sounds good. I think we're a bit ahead of schedule though, in 2 minutes.
Yes. Sorry. Yeah, 4 minutes. Yes.
Okay.
Well, thanks again.
I think I should have set this up so that it doesn't actually turn the screen off automatically. Ah. I wanted to print this, but I figured that my only printer doesn't really print colors, so I did what I could.
Yeah, that's this, my case here. So
Yeah. They seem to be black and white.
Yes. I use it my laser printer that is black and white.
That's a shame. I have a color ones, but I can hardly send them to you right now.
Nice. Yeah. They have these presenters kits with the colored versions of the cards.
Yeah, I have a presenter. I'm not quite sure why they are in the presenter kit because as a presenter, I'm not gonna do it myself. But...
Nice. You can moderate the moderators.
Super moderator. So just to be clear, do we have a hard stop at 45 past, or can we slightly overrun if needed?
I believe we can take a few more minutes. The interval is mostly to help the next presenter prepare.
Yeah.
So if
sure.
things are going smoothly, it is okay.
Okay.
If you need more time, you can ping Roman and ask him if he's okay with a smaller break sessions.
Okay, yeah, sure. But I think if it's taking too long, we can always switch to a hack room and continue there. It's probably a better way. Yeah.
Yeah, that works. Okay. Do you want to start a poll asking people if they are ready, or do we just start at the hour?
I guess we should probably respect the schedule.
Perfect. Okay. Yeah. I will do my best with my version of your bio, your biography.
Feel free.
Okay.
Yeah, I think we will have a few people joining.
Yeah. Well, let me start with the general information. Welcome to this session. We are following the anti-harassment policy of the Linux Foundation. So you need to be respectful on every comment and every question. Other than that, please feel free to ask questions during the presentation. You can either turn on your camera or ask on chat, and I will do my best to capture the questions and let Kevin know that there are questions. This talk will be given by Kevin Brodsky. He is a senior software engineer at ARM, and he has been mainly working on security features for the past 4 years, mostly Morello. And he's also one of those user space hackers who like to travel the boundaries of kernel and user space. Sounds like he's mostly living in the kernel space right now.
That's
Kevin,
right.
please.
Thanks, Luis. Okay, so so today I will be talking about Morello and the challenges of a capability-based ABI, which is really a long way to say that I want to put capabilities into the kernel, and that might be interesting. So first, let's talk about capabilities. So in this talk, I will be talking about Cherry and Morello. So first, Cherry is a hardware architecture that is part of a research project led by Cambridge University. So this project was started around 2012. And this project is centered around the concept of hardware capabilities, which are added on top of a conventional ISA. The first aim is spatial safety. So spatial safety basically means trying to prevent any kind of out-of-bound accesses, and therefore prevent exploits like stack overflow, heap overflow, return-oriented programming, all these things. And currently there is a shift also towards looking into temporal safety, which is the use after free class of exploits. I'm not going to talk really about temporal safety in this talk, but if you want to know more about this, there's plenty of resources. So Cherry has been implemented on top of two ISA so far, MIPS, and which was the first one, and more recently RISC-V. So now Morello is a research program which is led by ARM and funded by the UK government as part of a Digital Security by Design program, and also in collaboration with Google and Microsoft. So Morello is also a prototype architecture. So I highlight prototype here because in a rather unusual approach for ARM, Morello is not your standard extension that goes on top of ARM v8 in that case. Instead, it's really a research project that does not promise any kind of stability and has only one implementation, which is the Morello board, quite simply, which is a quad-core prototype implementing the Morello architecture. And really the main motivation for Morello, and in particular the board, is to allow for realistic performance measurements, which prove particularly difficult for the Cherry architecture in general because of its wide range, I would say. So in this talk, I will be slightly focusing on Morello, but really the vast majority is about Cherry in general. And Morello is really just, in a sense, one implementation of the Cherry architecture. It's not trying to overshadow Cherry as such. I strongly recommend, if you want to know more about the Morello program, to watch this talk by Richard Grisenthwaite, ARM's chief architect. Okay, so now concretely, what's a capability? So a capability is, you can think of it as a fat pointer ++. So first it has 128 bits of regular data. So a 64-bit value, the address. So this is based on a 64-bit architecture. The bounds, which are compressed to fit. The permissions, which restrict how a capability can be used. So if it allows loading, storing, executing, and so on. And an object type, which is something related to a concept called seal capabilities, which I'm not really going to talk about this today. So all these things can be set directly, either by writing in memory or by using the right instruction. Then on the side of this, there is what I would call a magic bit. So this is an unforgeable validity tag, which, so it will live next to your capability registers, next to the 128 bits of data, and in memory it will be stored separately in an implementation defined manner. So the very important thing about this bit is that it's not directly addressable. It cannot be set by software directly, at least, and an invalid operation will clear it. So basically, this bit is given to you at some point by the hardware, and the only thing that you can do is preserve it from capability to capability. So quick note: we say that a capability C is valid if its tag is set. That's what it means. So the rules of the game of capabilities. So the first rule, really the very principle of it, is validation. So whenever you use a capability as a pointer and dereference it, this will only succeed if first the tag is set, so if the capability is valid. If the access is within the bounds set in the capability, if the permissions allow it, and finally if it's not sealed, but I will not expand on that. The second rule is called provenance, and it's basically this idea that only specific instructions may construct valid capabilities. You can't create valid capabilities out of thin air. And in particular, arbitrary writes to memory will zero the tags in the corresponding 128-bit granule. Finally, we have monotonicity, which is this idea that bounds and permissions can only be restricted, not extended. You cannot add more permissions to an existing capability, not directly at least. So if you want to know more about this, there is an excellent overview by the Cambridge Lab, which is linked here. And I would like to note as well that there is a proposal to introduce a provenance-aware model in C2X, so the next C standard, which is clearly inspired by Cherry, I would say. Okay, so in practice, what do you do with capabilities? So there are two main language mappings for C or C++. The first one is called hybrid capability, which is really envisaging capabilities as a C extension. You can form capability pointers by adding an annotation. And in that case, you have to instantiate your capabilities yourself. And most of the time that means deriving them from global capabilities provided by the architecture. On the other hand, the other model is called pure capability. And in that case, we're really modifying the C model so that all pointers become capabilities. And in that case, your C runtime, the compiler, will make sure that everywhere you have a pointer, it's going to be correctly instantiated and derived if necessary. For instance, when you have pointers to the stack, or when you have relocations. Okay, so how do we use these two models? Hybrid cap is really mostly useful for specialized codes, so bits of kernel, LPC, and so on. And the main reason for that is that capabilities must be propagated explicitly. You need to add the _ capability annotation to all the pointers, that can be capabilities. And of course, existing library functions do not take capability pointers. So you have to have a pretty self-contained code base that uses capabilities. But it is less disruptive at runtime, simply because you have fewer capabilities, and so you're unlikely to get a capability fault unexpectedly. Now, pure cap, where all pointers are capabilities, is basically for everything else, for all normal software. As in not all software not doing too magic things. It's really the natural model for a capability architecture, because it gives you all the benefits of a capability checks. It will make sure that you will not go out of bound, that you do not write through a read-only capability, and so on. And for the vast majority of software, this requires no or very few code changes. But there is some runtime cost that, in fact, the Morello project will try to establish more precisely. And if your code base has bugs, then you will have to fix them because your program will just not run correctly. Yeah, and one last note. In low-level software, hybrid cap can be useful because it's kind of a transition before switching to pure cap, where you have capabilities everywhere, and that might be problematic. Okay, so now I would just like to touch on compartmentalization, because this is a very fundamental concept for Cherry Morello. So this concept of capabilities allows us to construct lightweight compartmentalization, which is basically isolating software components with the use of capabilities. And in that case, we would have every component in the same address space, but isolated thanks to capabilities. Instead of, if you take a browser currently, it will isolate the tabs using processes, which means different address space for each tab and usage of LPC, and therefore a lot of context switches. With compartments, we can get rid of a multi-address space, and we can potentially achieve much faster communication between the compartments. And by default, compartment can only access its own memory, and a compartment can grant access to its own memory to another compartment by passing capabilities. So there are many possible implementations. There are many usage models. This is really a topic that is being researched. And one thing that's interesting about it is it's really a strong use case of a pure cap model, because propagating capabilities is very hard in a hybrid cap model. And to get the benefits of compartments, you really want to be able to propagate the capabilities. So there is much more about this in the links at the bottom. A lot of work has already been done by the Cambridge lab on this. Okay, let's focus now a bit on the pure capability ABI, because this is really what this talk is focusing on. So really, the pure capability ABI is a bit of a paradigm shift, in the sense that, okay, your pointers are bigger, they're 16 bytes long. But I would say more importantly, they have this tag attached to them. So this is really a new ABI. You can think of it like 32-bit to 64-bit transition. Except that the other integers remain the same. It's transparent for most software, because they don't really need to be modified. The main exception here is really low-level software, so C runtime. Memory allocators really need to be modified so that they return capabilities with the right bounds and the right permissions. JITs also need to be heavily modified. if you want to use capabilities there. And in general, code making assumptions about pointers is likely to need some changes. So the main pain points for this kind of low-level software is so you need to have big enough storage, 16 bytes per pointer, aligned enough as well. So if you have packed struct, that may not work very well because your pointers must be 16 byte aligned. And the thing that is very relevant for Linux is that pointers cannot be stored in arbitrary integers. Only in PTRT or uint PTRT is valid. And that's because the other integers are simply not big enough, and the compiler will not keep the tag when copying them, even if they were big enough. Yeah, so bitwise operations can be tricky. In general, it is interesting in the sense that an address is no longer the same thing as a pointer. The addresses remain 64 bits, but the pointers and the in PTRT is now 128-bit large. So sometimes explicitly extracting the address from a pointer and reconstituting the pointer will be necessary. And certain patterns around memory allocation can be problematic. So some realloc usage is particularly problematic because it makes assumptions that it really shouldn't make. So if you want to know everything about PureCap, there is this Cherry programming guide that is a really good starting point. Right. So now the problem, the dragons. So the goal here is to support user space programs that are built in the PureCap ABI on Linux. So what this means is, well, first be able to accept capabilities. So being able to store all those user pointers as capabilities and give capabilities. But it also means to honor the capability metadata. So when user space passes pointers, now capabilities, the kernel must access the memory as if it was dereferencing the capability if it's not already doing that, which means respecting the bounds, permissions, and validity tag. Also, when the kernel returns capabilities to user space, it should at least ensure that these capabilities have the right bounds and permissions. mmap is a typical example. And yeah, finally, for the scope of Morello, we definitely would like to retain the base 64-bit ABI, so the existing ARM64 ABI. We do not require keeping the 32-bit ABI at this stage. It's worth noting that there is research into capabilities for 32-bit architectures, but this is very early and not really mature at this stage. So it's worth noting here that all of this has already been achieved on Cherry BSD, which is an adaptation of FreeBSD for Cherry MIPS and Cherry RISC-V. And yeah, so that it is possible, even though it may look a bit scary in a moment. So where are the pointers in the kernel user ABI? So they appear first obviously in syscalls, so in arguments, in struct members, and also in a few other places, so initial stack layout, around signal handlers. That's not anywhere as common as the syscalls. And in terms of how they are used, well, the obvious case is the user passes a pointer, the kernel accesses the user memory via copy to user, copy from user. So that's in the case of read or write syscalls, for instance. And sometimes it will access the memory via kernel mappings using get user pages. So that's the case for readv. A less common case is the kernel providing user space with a pointer. So as I mentioned before, a map can be also in argv put on the initial stack. And in some rare instances, the kernel will take pointers will take user pointers without really using them. That's the case for instance, for equal control and equal weights that accept some arbitrary data from user. So yeah, the first aspect of this is that, well, user pointers have to become capabilities. There's one good thing here is that in Linux, all user pointers should be annotated with an underscore user, so we kind of have a way to distinguish them, and we know where they are. And there is some hope for turning them into capabilities with some caveats that we'll come back to later. In any case, we will need a mechanism to enforce the bounds and permissions when using these pointers. But really, the main thing here is long. So long is everywhere on Linux. I don't think I'm really teaching anyone here. There is a strong assumption that long is big enough to hold any scalar type, so any integer, any pointer. And it's used to represent a lot of things, in particular addresses, which is fine, like in the MM code. But also pointers, which is not fine anymore. And sometimes it's used just as a catch-all type. So in syscalls, just take long at the root and return long. And then there's some magic to cast the types correctly. And this is particularly bad for multiplex syscalls like ptrace, fcntl, ioctl, especially ioctl, because at the top level you just pass along, and then your driver may do whatever it wants with this long, including interpreting it as a pointer. I would like to note here that there are currently 11,000 hits for long in include and 500 hits in include UAPI. So that gives an idea. That may sound slightly overwhelming. Okay, so what do we do to avoid this problem to start with? Well, a pretty natural idea is to have a shim, and in particular here, a user space shim. So, which really should be viewed as a stepping stone. So the idea is you have this this piece of code in user space that lives between libc and the kernel, and it does basically an ABI conversion between pure cap and the kernel's ABI. So just base ARM64 ABI in that case. It will do the checking. It will check that the capabilities passed to it to have the right bounds and permissions and so on. As much as possible. This is actually quite complex and sometimes can be difficult. Checking C strings can be racy. But we keep a completely unmodified kernel user ABI. And in terms of keeping the existing 64-bit ABI is very easy. We don't have to do anything. So yeah, here small illustration where we have the app code coding get kernel working directory with a capability. The shim checks the capability. It passes the pointer to the kernel. The kernel does its job. End of the story. This looks quite simple, but there are some pretty big flaws. The first one is there's no security boundary here. You can still do your raw 64-bit syscalls. And in fact, if the app does raw 64-bit syscalls, then obviously there's not going to be any ABI translation. So yeah, so it requires explicit checking of capability. That's extra cost. And also we need to know whenever the pointers are passed. And as I said, for ioctals, that's a problem. And yeah, so listed here, just in tree driver, almost 600 ioctal handler, and I'm not even counting the other tree drivers, would be complicated anyway. And finally, yeah, when the kernel stores user pointers, like in the EPOL case, or in the SIG-action case, or in actually quite a few other cases, well, the shim has to track and do the work of the kernel in a sense, but with capabilities. So it's not perfect, clearly, and it's actually quite flawed, but it's a starting point, and it works. Now the next step is maybe we could put this shim in the kernel. So really this is exactly the same principle, except that we're pushing the shim into Arch-specific code. We actually have a new kernel user ABI here, and we do enforce the security boundary because the shim is now in the kernel, so it can really reject invalid arguments. And so this has been attempted on ARM64, and also there is an experimental implementation in Cherry BSD. But here the complexity is that we would like to have PureCap as a secondary ABI. And really, the only way to do that on Linux is compat. Problem is that compat really assumes that you can fit your compat pointers in your native pointers, and you definitely cannot do that here because your compat pointers are bigger than your native pointers. So you could do this in other ways, but it is not actually very easy to do that. And in terms of limitations, it's actually very similar to the space shim, apart from the security aspect, because you still have your ioctal problem, you still have your explicit checking problem. So clearly, where I'm going to is what we would like to do eventually is just to fight the dragons, which means propagate the capabilities right down to where they are used in the kernel. So the consequence of that is that we have to say goodbye to long in many cases. Wherever a long can represent a user pointer, we didn't need to use a new type that can hold a capability. Naming is to be determined, maybe int user pointer t. And so quite clearly, this is an invasive approach. In terms of user ABIs, PureCap has to become a primary ABI for the reasons we've seen before, and 64-bit would become compat. And this is a cleaner approach, especially for U-access, so copy from user, copy to user, because user memory should really always be accessed via capabilities for specific reasons that I could talk about later if anyone is interested. Oh, by the way, if anyone can see an issue with compat being 64-bit, I would be interested. I'm sure that there are already some assumptions about 32-bit. I hope they're not very ingrained, but I may be wrong. So the first option here is to turn the kernel. Well, is the hybrid cap approach, which is turn the void _ user star into capability. It's a bit problematic because the annotation is on the wrong side of star. It should be on the right because it annotates a pointer. This actually might work because it's, and so making an _ user of a capability annotation could work. It's deprecated, but that's something that's worth trying. Should probably try that. Otherwise, maybe we could do some compiler magic here. I'm not too sure. There is a type for storing capabilities as integers in a hybrid. There is so there is a potential issue here because now the native syscall ABI will not be the same ABI as the kernel itself. And compat will actually be the native ABI of the kernel. So this is a bit weird. And there is a potential issue with UAPI headers. Should look into this. And so this general idea is what Cherry BSD currently uses, although not with the compat issue. Because Cherry BSD has multi. Hello again. Can anyone hear me? Hello?
Yes, we can hear you.
Yeah, I lost lost connection. So yeah, so it's the current approach used by Cherry BSD, which has multi-ABI support, so it's actually better there. And finally, the final option is just build the kernel in PureCap, which means all the pointers in the kernel become capabilities. This means replacing an awful lot more longs anywhere they can store a pointer. So it comes with all the benefits of a PureCap code in terms of, well, spatial safety, and also all the difficulties of porting the low-level code to a PureCap ABI, which are not negligible for a kernel, for a big kernel like Linux. And there is a potential performance impact, which really I would stress currently is not very well understood. And we need more data on this. And there is an experimental implementation of this in Cherry BSD. Okay, I'm slightly over time for what I expected, so I'm going to try to wrap up. Yeah, a few common issues, pretty much regardless of your approach used. In some cases, so I mentioned the get user pages case for readv. We will still need to have explicit checking because we don't actually access user space memory directly. Second thing is memcopy should not always copy tags ideally because we don't want to copy tags to user space, to copy capability tags to user space without really intending it. And yeah, the mmap interface is quite unfriendly with capabilities because once mmap returns a pointer and now a capability, it cannot change the permissions of a capability. So probably at this stage, we will have to return all permissions from mmap in the capability. There are proposals for basically a new mmap interface from Brooks Davis from Cambridge Lab. I've linked this at the bottom. It's very interesting talk with some history of mmap as well. Okay, so looking forward. So there are really two approaches to support this new PureCap ABI in user space. Either we shim with wraparound 64-bit syscalls, which is mostly non-invasive but requires very big switches to support things like ioctals and is overall quite fragile and quite hard to maintain, but is the easiest thing to get started. But really the more proper approach is to propagate, and that is make all the user pointers in the kernel capabilities. But it is quite invasive, and on Linux it particularly is. So really, yeah, supporting PureCap is painful in one way or another. But the propagate approach is really something that is, in the long run, is the right approach. And it has been done on FreeBSD, which, well, it's not the same thing as Linux. Has some better sides and some worse sides, so worth keeping in mind. Okay, so in terms of Morello, we will have a first release in October, I've put a link there. For now, it's basically a placeholder, but watch this space. It will, so amongst other things, it will have so core patches for Linux, for core support for Morello already, so registers, context switching registers, access to capabilities in memory, things like that, with a completely unmodified ABI. It will include a user space stream library, as I've described, and minimal Android with limited support for the PureCap ABI. Also, the Cambridge lab is going to release Morello support in Cherry BSD soon. I hear within the next few weeks. And now what we are going to start looking into is so a new kernel user ABI definition, which is really needs to be defined a bit more properly. It's not just about the pointer size. There are aspects to define a bit better, like the ELF marker, for instance. And along with that, starting to investigate this propagate approach in Linux. So if you want more information about the roadmap for Morello, I've linked to a talk about what our roadmap looks like. Right. So final slide. Some food for thought for people in general, even if you're not super interested about Morello or Cherry. There are some things in Linux that would be quite beneficial for this effort, and even not just for that. So some proper multi-ABI support will be nice, because compat is not really that. Start thinking about getting rid of longs and having more types, really. Because this is painful for Cherry, but this can be painful for a lot of things, and it's not really a good assumption in the first place. And finally, this minor point about having the user annotation on the right side of star. Okay, I've largely overrun my time. So please, if you have, here are all the resources here for reference. The slides are downloadable from the website as well. So if you have any question, any comment, any opinion in particular, I'm interested in them. And maybe we won't have time, but we can continue later, maybe in a hack room or somewhere else. Thanks a lot. Oh, I see that there are some questions. Hello.
Hello. We also have the problem with long and compat mode on some architectures where we need more type information.
Right.
To actually put the rate data into from the user space into the kernel. And obviously IO control has the same issue, like capabilities. So cleaning that up with more types is probably going to be very helpful in other contexts as well.
Out of curiosity, which architecture are you thinking about?
X32, the 32-bit variant of x86-64.
Okay.
The problem there is that the kernel API requires sign or zero extension of registers, but the user space calling convention says it doesn't really care in most places. So
I see.
You need to know the type in order to prepare the correct register content for the kernel.
Interesting. Yeah. Thank you. I see a question on the chat. Okay, so question about pointers. Well, pointers being bigger, basically. So to be clear, in Morello and the other Cherry architectures, there are registers that allow you to contain capability. Morello is actually a merge register file. So the overlap. But yes, there is a potential performance cost with having bigger pointers. It's not necessarily obvious because you also increase alignment in general, which is good for performance in general. It's really something that we're aiming to assess with the Morello board. I forgot to mention the Morello board is planned to land next year, end of next year.
Sounds like there is another question being typed.
Yeah, I'm seeing that.
Please remember, you can turn your camera on to ask questions.
Okay, yeah, so thanks Benjamin for that question. So a question about what do you do with IO devices? Yeah, so clearly when you interact with peripherals, you have to do something about your pointers that allow capabilities, and yes, you will have to extract the address most likely. So that's a bit more work. But again, I think if you have the right types here, then you will spot the error. The compiler will definitely help you spot the errors. Yeah, 3 minutes left. I thought saying that long is bad would be more controversial, but clearly, clearly that was not controversial enough. I'm a bit disappointed.
Kevin, we still have more 1 more minute. Would you like to have any final considerations? Would you like to take one more question if there are questions?
Sure. Well, I guess there doesn't seem to be any more question at this stage, but if you have any more question or comment, then please reach out. Well, either on Rocket Chat or my email is not there, but my email is just my first name dot last name at arm.com. I should be fairly easy to find.
Is there a general mailing list or IRC or something used for discussing this?
That's a good question.
Or is it LKML, I guess?
Well, the thing I forgot to mention is that at this stage we're not really targeting upstreaming because Morello is really a research program, and we're going to host the code on this.
Sure, but should we say some of us have to talk to you in public about anything? So make sure there's a nice public forum to do so.
Yeah, I understand.
Emails are out.
I think the Cambridge lab has something in place, and can't quite remember on top of my head, but I'll try to find out. Okay. Yeah, I will try to find out what the best channel would be, and I will put it there probably in a moment. Right. Well, thank you, everyone.
Thank you, Kevin. Thank you for the talk, and thank you for the polemic subject, the loan sharks.
That's a pleasure.
Okay, we will have a break, and we will back on the hour. Okay, for the next talk from Roman. See you there.
Hi, Lewis.
Hi, Roman.
Hi, do you hear me well?
Yes, pretty well. You have now the presenter's rights, so you are the presenter.
Oh, okay, thanks.
If you want to test the slides and see if everything is working.
Okay, yeah, looks good.
Nice. We can start in 5 minutes if you don't mind.
Cool. And like, should I leave this session and join my own, or it just will continue?
Yeah, just continue. I mean,
okay.
everything is in place. Yes.
Okay, perfect.
I just need to make the formal announce of the starting of the session and remind people of the rules, and that's it.
Okay, cool, yeah.
Oh, by the way, how is pronounced your last name? Just to be sure I got
Like
it right.
Gushin. It's a complicated Russian letter, yeah. It's actually in Russian. It's just one letter. Like it's like sh.
Perfect. Yeah, but I mean that's a sound that I can reproduce, so that's great.
Thank you.
Yeah, sounds like people is arriving for the session. So you did something fantastic in the name of your talk, because usually people look at the name of the talk and decide whether they are going or not. And with that 40% comment, you got it. Congrats.
Thanks. Yeah. Yeah, but it's like, yeah, nobody cares about kernel memory counting without this bonus.
Okay, can we start?
Sure, yeah.
Okay, so good morning, good evening, good afternoon. Welcome to this session. Roman Gershon will be presenting recent changes in the kernel memory accounting. Roman is a software engineer at Facebook, at the kernel team, and he is mostly focused on the memory management and Cgroups. Just remember that you can ask questions at any moment. Please turn your camera on and ask your question, or you can use the chat to ask questions too. So please, Roman.
Yeah, thank you, Luis. Thank you, everybody, for having me. So today I'm going to tell about some recent changes in the kernel memory accounting stack, which I've been working on for the last couple of years. I'll start with a short description of how the stack looked 2 years ago when I started this work, what was good, what was not so good, what kind of problems we've seen, and what we did over these 2 years to address them. So 2 years ago, the kernel memory accounting was already an essential part of the memory Cgroup isolation. It was on by default on both Cgroup v1 and v2. And it was a system-wide feature, so it couldn't be turned on or off on individual Cgroup level only as a system-wide feature. In general, the design resembles the design of user space memory accounting. So most of it was implemented as a part of the page allocator. So page allocator basically at the very last moment before returning the page to the callee, it was checking the JFP flags, and if JFP account was set, it was charging the current Cgroup with the size of the allocated page. And in case of success, the memory Cgroup pointer was saved in page memcgroup field, struct page memcgroup field, and the reference counter on CSS object of memory Cgroup was increased. So that basically means that every charged page was pinning the original memory Cgroup, and it means that memory Cgroup can be destroyed until there is at least one charged page. As we can see further, it is a very important property. Like slab memory, slab objects are obviously usually smaller than a page, so to account them on the page basis, as the following trick was used. The whole slab or slab infrastructure was replicated for each memory Cgroup. It means that every memory Cgroup has its own slab caches, its own slab pages, and they were never shared between different memory Cgroups. The process of creating this replicated infrastructure for each memory Cgroup is quite complicated. It can be done from, like, I don't know, interrupt context or just a critical section. So that part was done asynchronously. So like the first allocation triggered scheduling of delayed work, which created a separate slab cache per memcgroup slab cache, and this slab cache can be used for following allocations. So like first few allocations were passed unaccounted, and following allocations can use this slab cache. This part of code was quite hairy because there are like root and per memcgroup slab caches. There are individual slab allocations, and there are memory Cgroups, and all these are dynamic objects with their own lifetime. And there are different kinds of problems when, I don't know, an allocation triggers the creation of slab cache, and during the creation, the Cgroup is deleted by a user, and like that part was quite hairy, and we had a number of bugs over years in this part. But other than that, as you can see, the design was pretty uniform and nice, I can say. Socket memory accounting was an exception and still is an exception. It was done completely independently. It was implemented using a couple of hooks from the networking stack. It didn't use page allocator. So it's a complete exception, and it's in the same state right now. So I won't touch it anymore today. So what was not so good? Like the first problem we've noticed was the so-called dying cgroups problem. First of all, what is dying cgroup? Dying cgroup is a cgroup which has been deleted by a user but stays in the kernel memory being pinned by something, by, I don't know, a page cache page or slab object or whatever else. Why it's a problem? There are two aspects. First, not all cgroups algorithms were scaling very well with the growing number of cgroups, and mostly we fixed this over the whole tree, so now it's less of a problem. The second aspect is just the memory footprint. So cgroups in general and memory cgroups in particular are quite large objects. Like memory cgroup on a moderately sized machine can be like 100 kilobytes. On a really large machine, it can be like 1 megabyte large. This is mostly per CPU memory, per CPU statistics and event counters and data like that. So if you have thousands of dying cgroups, it means that you're wasting gigabytes of memory, and this is mostly per CPU memory, which is unmovable, and you have all kinds of fragmentation issues. And this is exactly what we've seen in our production. So in the real life, the number of dying cgroups grew pretty much on every host in our fleet. No matter how big the memory pressure was. Like, it was not just like a monotonical leak. Sometimes under very heavy pressure, it went a little bit down, but in general, it grew over time pretty much everywhere. I gave a long talk about this problem a year ago on the last LSFMM summit in Puerto Rico, and now I will just shortly repeat two aspects of it which are connected to the kernel memory accounting. So the first part of it is related to accounting of kernel stacks. So these days, kernel stacks can be backed by three different options. Like, one is generic pages, the second is slab objects, and the third one is vmalloc based, just vmallocs basically. It depends on your configuration and on your architecture. Basically, is the ratio between the size of your page and the size of kernel stack. But on typical configuration on x86 now, it's kernel stacks are vmalloc based. So the problem with vmallocs is that they are relatively slow. So in order to speed things up, we have a small per CPU cache for 2 stacks. So the idea is simple, like on exit, a task can drop its stack to this cache if there is an empty slot, and the next clone on the same CPU can just grab it and use, and it's very fast. So, but there is an obvious problem with accounting. If the accounting is performed by the page allocator, it means we're charging the stack to the first cgroup when it was allocated first time, and then we pass it to some non-related process in other cgroup. It means that we first we screw accounting up, and second we pin the original memory cgroup with some non-related third-party process. So in order to fix this, we obviously moved the accounting from the place where we allocate and free the stack to the place when we assign it to a task and when we take it back. So this was the first breakage of the uniformal rule. The second problem was harder to fix. It was related to slab objects and in general and mostly VFS cache, inodes and D entries. So in the original design, the idea was that once the cgroup is deleted by a user, the memory pressure will eventually reclaim all associated slab objects and corresponding slab pages. That means that the reference counter on the memory cgroup object will eventually reach 0, and it will start a fairly complicated process of cgroup destruction. And as part of it, we will destroy the whole slab infrastructure, slab caches, and so on. So the problem is that, like in the real life, some of these objects can be used by different C groups, by processes in different C groups, and after the deletion of the original memory C group, they can not become even like a little bit colder at all. Like they can be as hot as it were before, or even hotter, or they can be even pinned in the memory by something. And because we need that just one object to pin the whole memory C group and the whole slab infrastructure in place, this is exactly what was happening in the real life. Imagine, for like quite simple example, system D, like system D is running some workload and it's getting restarted periodically, maybe just because it's crashing, or I don't know, the binary is getting updated, or new arguments are passed, whatever. And every time system D is creating new memory C group, and the new workload starts in it, it's scheduling, creating a new slab caches, new set of slab caches, and some objects are used from old memory C group, and some objects are recreated in a new memory C group. And it means over time, over time, your working set is getting split over multiple generations of the same C group, but it's the same for us, not for the kernel. For the kernel, these are completely independent instances of the same C group. Yeah, I see Shakil is saying that the same problem. We have the same problem with page cache. It's true to some extent. Like with page cache, we have a hack in place, which basically applies extra memory pressure to abandoned C groups with only few pages left. If I remember correctly, the number is 16. If we have less than 16 pages, we try to scan like 16 pages all the time for deleted for dying C groups, and it helps a little bit with reclaiming. So actually, I mean, I'm absolutely agree that page cache is also a problem, but in the real life, it's a little bit less of a problem. But probably we can use some ideas from the kernel memory accounting to page cache as well in the future. So going back to VFS cache, so how did we solve this? We introduced the idea of slab reparenting. What does it mean? So the idea is simple. When a user deletes a C group, we can recharge all slab pages to the parent C group. The only problem how to do it efficiently. Basically, we need to iterate over all slab pages and replace the memory C group pointer to the parent memory C group pointer and adjust reference counters. But in the real life, we don't even have a comprehensive list of slab pages in some cases, and you know, we would have all kind of locking problems. But we don't really want to make this process expensive, so we did the following trick. We moved the memory C group pointer from slab page level to slab cache level. Because the relation between slab pages and slab caches is stable, we never move past pages between slab caches. It's a valid operation. And also, we did invert their owning scheme. So as I said previously, the scheme was individual pages were holding reference to the memory C group, and the memory C group was owning the whole slab infrastructure. And in the new design, individual slab pages were owning their corresponding slab caches, and these slab caches were holding a reference to the memory C group. That allowed to actually release empty slab caches before the corresponding memory C group, and release the memory C group with outstanding slab objects and slab pages. So the new scheme was much better in terms of garbage collecting efficiency, but the problem was that the code becomes even more complex and even more hairy. Anyway, it was merged into 5.3, so about like slightly more than a year ago. And when I was working on this problem, just coincidentally, I was debugging some non-related issue. I don't even remember what it was. And I remember I was just was SSHing to some host, and on that host, I looked into proc slab info, and I noticed that there are 400,000 of active task structs. And looking at other, like at PID numbers and just like PS output, it was hard to believe that the host is running 400,000 tasks. So I started digging in, and I found out that the number of active objects displayed by proc slab info is not true if you are using slab and you're using slab CPU partial lists, which is a default option these days. And if you use slab and this option, the slab utilization as shown by proc slab info is usually like almost always in high 90s, but the real numbers should be much lower. So in order to get a ballpark approximation of the real number, I wrote a Dragon script which just iterated all over pages, slab pages, and counted the real number of active objects. And when I got the real numbers, I ran the script like on many different machines running different workloads in our production and just my own desktop. And real numbers were quite shocking, I would say. So the best number I've seen was 65%, and the worst number I've seen was like 15%. And it means that the real memory overhead of kernel memory accounting is not like 0.2%, which we would expect from having just one memory Cgroup pointer per page, per struct page, but it's somewhere around like 50%. And to check this hypothesis, I just run same workloads with disabled kernel memory accounting and run the same Dragon script and check that the memory slab memory utilizations went back to high 90s, and the total size of the slab memory reduced almost twice. So at that point, it was clear that we need a new way of for accounting slab memory. The current way is way too expensive. And we need a new Cgroup slab controller. So how it should work? So the obviously the simplest way to get back the slab utilization is to get back the memory layout. And the obvious way to do it is to return back to using the same set of slab caches and slab pages for all memory Cgroups. And that means that we need to move the accounting, like mem-Cgroup level accounting, to an upper level and account individual objects instead of individual slab pages. And obviously, we need to keep reparenting working, because the dying Cgroup problem is not going anywhere. So what should we do to implement this? Like, the first question is to where will we store the ownership information, right? Previously, we had this per page pointer, and now we should have a per object pointer, and we should place it somewhere. And there are two obvious options, like the first option is to squeeze it to the end of the object, which has some pros and cons, as all other methods. And the second way is to have some external place. In the current implementation, Okay, so in the current implementation, I went the second way. So for every Slab page, I have an external array of pointers, which is attached to every page, and I'm reusing Slab Cgroup pointer, which is not used anymore for Slab pages, to point at this vector. But we can arguably change this way in the future. There were some clever ideas by Shaquille how to reduce the memory size even more by putting this vector into struct pages of compound pages. The second question, which so here is how the new struct page looks like. So as you can see, there is a vector not of memory cgroups, but object cgroups. I'll tell you further what it is. So the next thing is, because we should account individual objects which are smaller than a page, we should account in bytes, not in pages, and all the existing memory cgroup code and corresponding APIs, they all handling pages. So one obvious way to fix this was to switch everything to bytes, but that would be really expensive, especially on 32-bit platforms. So that was really not an option. Instead, what we did, we built a layer on top of the existing charging mechanism, which basically borrows some pre-charged pages from the existing API, splits it over for multiple Slab objects. It uses per CPU stocks, similar to how we batch the existing page size at charging. And the third thing is reparenting. So we should keep it working. So saving directly memory cgroup objects and increasing their reference counter for every charged object is not an option, and we don't have this Slab per memory cgroup Slab cache, which we used as intermediate object previously. So we introduced some new type of this intermediate objects, and we call it object cgroup. So basically, object cgroup is like some sort of counting vessel, which we use in a way similar to memory cgroup. So for current memory cgroup, you can get the current object cgroup. You can increase its reference count or decrease its reference counter, and you can charge it and uncharge it for some amount of bytes. And object cgroups are reparented to the parent memory cgroup when the real memory cgroup is deleted. So object cgroup is an object which can be used to store the memory cgroup ownership of long-living objects. For statistics, for VMstat statistics, we went a slightly different way. We just converted to Slab-related statistics to bytes. It's actually a little bit more complicated than that. So we have the statistics on multiple levels, like on node level and memory group level, or more specifically LRUVEC level, and we did different things for different levels. Unfortunately, it was done that way just for performance reasons. The thing is, for global statistics, we count Slab pages. We don't count Slab objects. We only are interested how many Slab pages per node we have and per zone. And for memory cgroup level, we account individual objects. So how it all works in the real life? So actually, it's working pretty well. My initial concern was that the new scheme will be better in some cases and worse in some other cases, and it's easy to understand because having one pointer per page is obviously better than having one pointer per object. But in the real life, the quite opposite was true. So we've seen significant memory savings all over, like on every host we use it. With Slab, the typical number is like 40% of the Slab memory, sometimes more, sometimes over 50. I have to say it's actually a hard question how to measure this percents. There are several aspects of it. Like first, if you free up some memory, the kernel tends to fill it with caches, including VFS cache. So the fewer Slab pages you have, the more Slab pages you have. So it's sort of a bad loop. This is one thing. And also, like, probably we should measure it under like a constant memory pressure, and it's fairly complicated question how to do it properly. So we did a lot of measurements on in the real life on real production hosts, and also the simplest way just to get a ballpark number is just to restart the host and look at how big the Slab memory size is just after booting the system. So for Slab, as I said, it saves about 40% of the total Slab memory. So I think it's pretty significant. For Slab, the savings are less significant. But still about 10 to 15%. It's mostly because with Slab, the initial problem with Slab utilization was not so bad, so it was much better than initially. And in absolute numbers, in our production, we are saving from high hundreds of megabytes to a single digit of gigabytes per host in our Facebook production. So it's not bad at all. As an additional bonus, which is also nice, because there's like Slabs unmovable memory, and we have like by 40–50% less Slabs. The memory fragmentation is getting smaller too, and the total set of Slab pages is getting more stable. So earlier, when you delete C groups and create new C groups, restart workloads, there was always a need in creating new Slab pages and slowly moving Slab objects from old Slab pages to new Slab pages. And now, if the total size of Slab memory is not growing, like there is no need in allocating new Slab pages, so it's way more stable. The second concern was CPU regressions. Obviously, counting individual objects is it's a more granular accounting, and it requires more CPU cycles. But in the real life, we haven't seen any measurable regressions so far. But let's see if we will see it with upstream kernel, but hopefully no. One other nice aspect of it is that in general, the new design is way simpler. So because all this part related to dynamic management of per memory C group Slab caches, its creation, destruction, all of it is gone. The new implementation is way smaller and in general simpler. There are some hard parts, but not so many as it were before. So the patch set was mostly red. And as a last bonus, the introduction of APIs and code which allowed per object memory counting allowed to introduce the accounting of per CPU memory. So in earlier days, per CPU memory was not accounted at all. And with the growing number of per CPU memory users, it's becoming a problem. For us, two biggest users are BPF. Some BPF maps are backed by per CPU memory, and just the user can directly allocate large chunks of per CPU memory. And the second user is C groups. So C groups code is using per CPU memory quite intensively. If we have a lot of C groups, including dying C groups, we have large portions of per CPU memory allocated. So on our machines, it's typical to have like high hundred of megabytes, sometimes even gigabytes of per CPU memory per host, and not accounting it at all creates a hole in memory isolation, in Cgroup memory isolation. Because per CPU object by its nature, it's split over multiple pages, and potentially it can take only a small part of each page. Accounting them on per page basis with the old paradigm was very problematic. But with the new scheme, it was really straightforward to implement. So it just basically, I use the same design which I use for slabs accounting. I use the same design for per CPU memory counting, and it went pretty straightforward. This patch set was also merged into 5.9. Yeah, I probably missed that. Like all this slab accounting stuff, it was merged into 5.9. So very soon you can try it. You can try it on a vanilla kernel. As now there is only one example of per CPU of an accounted per CPU memory. These are some Cgroup internals which are charged to the parent memory Cgroup. And it means that if you have now like a Cgroup with, I don't know, thousands of child Cgroups, it won't be empty from the memory perspective as it was earlier. It will show you the real price. And arguably the next use case will be BPF maps, which I'm working on right now, and it will hopefully be merged into 5.10. So as you can see, there were a lot of changes during these 2 years in the kernel memory counting stack. Now it's significantly less expensive. It's not taking 50% overhead anymore. At the same time, it's less uniform, which to some extent it's a drawback. Not everything is, as you saw, like not everything is now done by page allocator. Some things are tracked by per page basis. Some things are tracked on per object basis. MemCG reference counting scheme is not so uniform anymore. Like we have reparenting, but at the same time, I believe that this like reduced uniformity, it represents the actual different properties of different types of kernel memory. So it's not a bad thing. And it's, as I said, it's significantly more effective, and it has fewer garbage collection issues as well. So as the last thing, I just want to thank a long list of people who helped me with working on these patch sets in different ways, by reviewing, by contributing their code, by sharing ideas, and so on. Thank you very much. So that's pretty much it. So I see a question by Greg. Sorry, Greg, I'm not sure I fully understand your question. Maybe you can get online and elaborate a little bit more on it.
Can you hear me?
Yes.
The question is just, if the supposition is that we have sort of referenced memory that was previously pinning these expensive mem groups, that presumably lives on. It's just much smaller than the C groups. And if that referenced sort of slab memory or K memory in general sort of lives on and grows from day to day, system administrators might get kind of annoyed that there's this sort of unattributed memory that's been reparented to the root memcg, presumably, that has no longer any linkage to the original job which allocated it. And that could represent some optimization that someone would want to make, some application change that would be yield to better production operation. But there's no way to know which job actually allocated this memory that's now sort of lingering at the root level.
Right, but like I don't see a better option right now. So the problem is that, as I said, memory Cgroups, it's a very large object, and if it's pinned, like it can be, say, for example, 1 megabyte, and if it's pinned by object which is like only few bytes in size, it can be easily like 1 to 1,000, if not 1 to 10,000 ratio. And in general, we think that having like I don't know, thousands of not very hot inodes, for example, it's not a big deal, and it's in general better to have them rather than to over reclaim them and have some sort of performance regression. So I don't know. I mean, if we can figure out a good way to actually recharge this object to an object to a different Cgroup which is more actively using them, that would be really nice, but it's really complicated. So it's like it's a common problem of memory Cgroups related to accounting objects which are shared between memory Cgroups. We don't have a good solution for it.
Yeah, my only idea was to leave behind a much smaller proxy for the original mem Cgroup that wasn't a megabyte, that just represented its name or its identity.
Oh, maybe, yeah, maybe. Actually, like the reparenting is kind of the same idea. I mean, I'm still having this object Cgroup or slab cache in the previous version, which was exactly this same, the small object you are talking about.
Okay, thanks.
Are there any other questions?
I had a question about the page cache accounting. Can you hear me? Yeah.
Yeah.
So as I understand, this is charged to the first user always, right? So if there are like containers sharing the same file system, whoever started first is charged the most of it, right?
Right.
Is there any, I don't know, a development to have a shared page accounting, or like any ideas about that? Is that a problem at all? Like,
it is. I mean, it's completely unrelated to this talk, but
that's right. But
yeah, okay. I think I was like personally, I was participating in some discussions around it. So some ideas I'm familiar with are like my own idea is that we probably should abandon the idea to count page cache on individual page level and decide to count the whole inode with all corresponding pages to a single Cgroup, and then we can, then it will be much easier to implement recharging to more active users, something what we do with dirty memory. That is one way, but yeah, it's just an idea. I never tried to implement it, so there will be, I'm sure there will be hard questions to answer. And the other idea I remember discussing was to implement some sort of a special per page flag, which will basically mention that the page is abandoned by the original memory Cgroup. For example, we can set this flag automatically for dying Cgroups, and then the next Cgroup who is using this page should get it charged before starting using. So I think this is a clever idea which can help us in some cases. It does not address the case when there is a inode which is actually used by many Cgroups at the same time, but it hopefully will address the case when we sort of pass a page cache address space between multiple Cgroups.
Yep. Thank you. My second question is even less related to the talk, and I'm not sure I should ask it. But yeah, let me try and just say no. The question is about the ARM killer, and obviously that it tries to figure out which cgroup to kill, which process to kill. It looks into those counters, and if you know, can you tell me if it takes into account that many objects are reclaimable in there, and it does count the reclaimable objects such as the entry page cache and all this?
So as now the killer is not working on MEMC group levels. It's only can kill it. It does not use MEMC group level statistics for choosing the victim. It can only kill the whole process, the whole cgroup of the selected process. I spent a long time. I was working actually on this problem, like, I don't know, 3 years ago. I sent a number of versions, but we didn't come up to an agreement on how this should, how just the policy should look like, how to iterate over cgroup tree and so on. So as now, yeah, the killer is not MEMC group aware in terms of selecting the victim.
Okay, thank you.
Let me, I think, come back to the question in the first question of Kirill, I think, was the page cache issue, right? So I think we also discuss about the memcg, like the mount option, like having a memcg attach to a super block, something like that. Internally, like in Google, we kind of have this option for tempfs files, which is shared between multiple cgroups. So that's kind of another way. Like, so you know which are the file systems shared between, the admin knows which are the file systems shared between multiple cgroups. The admin can attach maybe the common root or a special cgroup which is a kind of common, which can be charged, or like you dedicate the resource to that particular like page cache from that mount option or that file system, and then all the cgroups can share there. That's another option to do that.
Yeah, I agree. So in general, I think it's just like if we have a memory cgroup per page, it's a very granular accounting, and I mean it's good from one point of view. It's a good thing to have such granular accounting, but from another, because we have so many cgroup pointers and they're disconnected from like higher level objects, it's very hard to like do anything with this memory cgroup pointer once we've allocated it. So if we have this pointer at higher level, at inode level, or even at superblock level, it's much easier to do something with this pointer.
So I have questions, or like, let me just throw out two questions. So I think with your changes, you are also planning to enable the accounting within the interrupts. Can you tell more about that? And second question is more on the, like, the kernel used to do opt-out KMM accounting, but now it switched to opt-in. Do you see if after all these changes, what you're doing, we can go back to the opt-out?
Shakil, can you please repeat the first question?
First, the interrupts. Currently, these allocations are not MEMC charged if you are doing allocation within the interrupts.
I see.
The bypass, KMM bypass.
I see. I think from like, it's not hard from the kernel memory accounting code to support them in terms of like locking and performance overhead. It's fairly simple. The problem with I see is like more, do we know, do we want like which cgroup should be charged? Like, do we have examples of interrupts when we have a significant memory allocations and we know exactly which cgroup should be charged? if there are some examples, I think it's pretty straightforward to add them for accounting, but I'm not aware of such allocations. So from my perspective, like network allocations can be example, but it's really hard to say which C group should be charged. Oops.
We have the SKB linked to the C group, right? The SKB.
Maybe, yeah. Yeah, but yeah, I don't know if it's incoming traffic. I don't know at which point we we get this like association with the memory C group. And the second question related to opt-in or opt-out, yeah, I don't know. I mean, honestly, I don't have any opinion here, so I don't like I don't have any good metrics which shows like if we have a significant hole in memory counting. It looks like we cover most significant objects, but I'm sure there are some missing parts as well.
Sorry, the time is up. Roman, if you want to keep discussing, we can create a hack room or even both for the discussion. I can help you set up this.
Okay, yeah, I don't know if there are any questions left. We can sure. Yeah, I'm open. If somebody has any question left, I'm like, you can chat me in private and we can discuss it. I think it's the best option. Thank you, Luis.
Okay. Well, thank you, Roman. Thank you for the talk. It was really interesting, and I'm waiting for my 40% of memory back. Okay. Thank you again. Thank you.
Thank you for having me. Thank you. Bye.
Thank you to you all that participated today. See you again. Bye bye.
You are currently the only person in this conference.